Hello, and welcome to the NLP Highlights podcast, where we talk about interesting work in natural language processing. The hosts are members of the Allen NLP team at the Allen Institute for AI.
Okay, for this episode, we are going to talk about this paper that I read on Archive recently called Prefix Tuning, Optimizing Continuous Prompts for Generation. And to talk about this paper, we have with us Lisa Lee, a PhD student at Stanford. Welcome to the podcast, Lisa.
Hello, Pradeep. Thanks for inviting me, and thanks, Anna.
We also have with us Anna Marasovich, a co-host for this episode, who is a postdoctoral researcher at Allen AI on the Allen NLP team. Welcome, Anna.
Thank you. Hi, everyone.
Okay, so let's talk about prefix tuning. So, Lisa, can you give us an overview of what exactly prefix tuning is?
Yeah, sure. So from a high level, prefix tuning is a lightweight alternative to fine-tuning for natural language generation tasks. So for example, if you want to adapt your pre-trained GPT-2 model to like a downstream generation task, such as summarization, a common practice would be to fine-tune your pre-trained model on some selected dataset and save the fine-tuned model copy. However, one caveat is that when the model gets very large, to a scale of GPT-2 XL, or even to a scale of GPT-3, then storing the entire model copy is going to be very expensive, especially if you have many tasks that you want to adapt to, since you will need to save a different model copy for each task. And now prefix tuning can come to the rescue because it is very lightweight, since prefix tuning keeps the language model parameters frozen and instead only optimize a very small continuous vector for each task. And this continuous vector is called the prefix, which we prepend to the beginning of the generation as if it were virtual tokens. So one interpretation of prefix tuning is that we are learning a continuous prompt or a continuous task instruction for each task. And the number of parameters in the prefix is 1,000 times fewer than the full language model parameters. So for example, it can take only around 250K for each additional task.
That sounds great. Yeah, thanks for the overview. In terms of doing or making fine-tuning more lightweight, I'm aware of a couple of other techniques for doing that as well, including lightweight fine-tuning or fine-tuning only a subset of the weights in the model. How exactly does prefix tuning compare with some of those other methods?
Yeah, sure. So like to compare with other lightweight fine-tuning approaches, like the most popular one is adapter tuning. Adapter tuning would lead to 30 times fewer trainable parameters than fine-tuning, while maintaining a comparable performance. Whereas prefix tuning has a more drastic reduction. Prefix tuning leads to 1,000 times fewer parameters than fine-tuning, while still maintaining a comparable performance. So it is much more storage efficient in that perspective. And like for other methods that are also lightweight, such as the masking idea, where we can train a binary mask over model weights and decide which mask to drop and which mask to keep for different tasks. I think in that case, the reduction is also around 30 times or 32 times, because it's essentially reducing a floating number to a bit, like reducing a 32-bit thing to 1 bit. In that case, it's also around 30 times reduction, which is a lot smaller of a reduction than prefix tuning.
Cool. Yeah, that sounds good. Since you mentioned adapter tuning, and I know that some of your experiments in the paper compare against adapter tuning.
Mm-hmm.
I wanted to understand that more. Can you tell us how exactly adapter tuning works?
Yeah, sure. So adapter tuning essentially just inserts adapter modules in between language model layers. So adapter modules are like some MLP layers, like some 2-layer MLP that has some nonlinearities in between. And then the idea is that if we insert the adapter modules between each language model layers, at training time, we would freeze the language model parameters and only train those adapter layers. And at test time, you only need to store the adapter layers, which leads to the reduction in parameters storage.
Okay, yeah, that makes sense. And I guess we'll talk more about how exactly prefix tuning compares with adapter tuning in a few minutes.
Yeah.
Let's talk more about the details of prefix tuning then. You've given us an overview. Can you tell us more about the details of how exactly prefix tuning works at training time and test time?
I think actually, like before we start talking about that, we could talk more about like GPT-3 style prompting, because that would like lead naturally to the intuition of why prefix tuning might work, and then some trade-off in between.
Sure, that sounds good. Yeah, please go for it.
Sure. So GPT-3 actually lies on the other extreme. GPT-3 and its in-context learning framework means that people can write down some task instructions and give some examples as demonstrations to prompt GPT-3 to generate some output. And indeed, GPT-3 kind of get away with the problem that we mentioned above with fine-tuning, that we don't have to save any large fine-tuned models at all, because we don't even need to do any training or parameter tuning when we apply in-context learning. Instead, we just need to write down different prompts for different tasks. So we don't need to save any parameters at all, essentially. However, in-context learning will introduce some other problems. Like first, we couldn't exploit very large training sets because GPT-3 has a bounded length context window. That is, it can only attend to a bounded number of tokens. So when we have a training set that's longer than the context window, in-context learning cannot fully exploit that training set. Whereas the second disadvantage is that we have to manually write up the prompt. For example, we have to write down the instruction and we have to select some demonstrations. However, this manually written prompt may be suboptimal. And the third disadvantage is that in-context learning seems to be quite unique to GPT-3, and it does not generalize to smaller models like GPT-2 or BART. Whereas prefix tuning kind of addresses all the above issues in context learning by having this prefix to be trainable. So when we train the prefix using gradient-based method, and gradient-based method can easily scale to large training set. And also, since the prefix is trainable, we don't have to manually specify them. And therefore, the trained prefix or the learned prefix is going to be more optimal than the human written prompt. And furthermore, we apply prefix tuning to smaller models like GPT-2 or BART, whereas in-context learning is kind of limited to large models like GPT-3. So that's kind of the intuition of prefix tuning, or where the motivation comes from. And then going back to our question about precise details of what we did to during training, or what prefix tuning is exactly doing. So let's first give one small intuition. So if you want to steer a language model to generate a particular word or phrase, this is true even for GPT-2 or smaller models. So say that you want to generate the word Paris, for example. One solution would be to update the model parameters to increase the probability of P Paris. Another possibility, which does not require any parameter update, is to prompt the language model with a good context, like the capital of France is blank. And then it will naturally fill in Paris with a high probability. So the takeaway here is that by conditioning on the proper context, we can steer the language model to generate a particular word. And we can extend this intuition to generate a particular phrases or sentences. And in prefix tuning, the goal is to further extend this intuition to a more useful setting. Like, can we find a context that can steer the language model to solve an NLG task? So in the paper, we actually implement prefix tuning for both GPT-2 and BART. And here, let's just use GPT-2 and the table-to-text task as an example to show how it works. So in a table-to-text task, let X the data table and Y denote the textual description of the table. And prefix tuning initializes a trainable matrix P theta, which is parameterized by some theta parameters of the dimension prefix length times the number of activation vector times the dimension of activation at all transformer layers to store the prefix parameters. So when we compute the activations at each time step for the first prefix length number of time steps, we directly copy from the prefix matrix P theta. And for the subsequent activations, we will use the recurrence formula defined in the autoregressive transformer model. Basically, it means that we will use the pre-trained attention mechanism to attend to all the activations in its left context. And at training time, the objective we optimize is the same as fine-tuning objective, which is the cross-entropy loss of the y given x.
Right. So just to confirm that I understand what's happening here. In contrast with GPT-3 style few-shot learning, what you have is that you still have a prefix here, but as opposed to the GPT-3 style manually written prompt, you have a continuous prompt which you're learning.
Yeah,
correct?
Exactly.
Right. And regarding that, right, I know we've talked about some details, and I'll get into the details in a minute. A couple of questions about that difference. You mentioned that the manual style prompts work only for GPT-3 style models or large models like GPT-3, but you didn't see that working for smaller models. Can you elaborate on that? Why was that the case?
It's more of an empirical result. So like people have shown that, or the GPT-3 paper has shown that like if you prompt it with like the right task instruction and the right few shot examples, then GPT-3 is going to naturally generate some continuation that would be a very meaningful output. Whereas if you try to apply the same setting to GPT-2, so if you prompt GPT-2 with some task instruction, some few shot examples, then GPT-2 does not generalize well. So like GPT-2 will probably just give you some copying operators from the context that you give instead of actually extrapolating to the new input that you really wanted to perform the task on.
Okay, that makes sense. And right, the other distinction I think that's maybe worth reiterating is that unlike GPT-3 style prompts, your prompts are continuous, right? I mean, they're not interpretable. They don't correspond to specific words in the vocabulary.
Yeah,
correct?
Right. That's right.
Right. And does that like make your prompts less interpretable than GPT-3 style prompts?
Yeah, exactly. It will make the prompt less interpretable because the prompt now is a continuous vector. And then, so I think there are two aspects that we can consider here. So suppose that we are really doing discrete optimization, as in the auto prompt paper, where instead of doing continuous optimization and learning a continuous prompt, they are doing discrete optimization and learning a set of discrete tokens. In that case, the set of discrete tokens is also not interpretable. I mean, you can interpret it because there are words in the vocabulary, but putting them together, they are not meaningful English sentence either. So it kind of shed light to a possibility that maybe the most useful prompt setting when we try to optimize it aggressively for one task is not going to be interpretable, or it's going to be a bit strange in the wording.
Can you tell us a little bit more about how is prefix tuning different from conditional generation models like control, where we have some kind of, as well, prefix, but like actual word, like summarization, semicolon. And there we also have a continuous representation. It's the embedding of the word summarization, right?
Mm-hmm.
Can you specify a little bit how prefix tuning is different from that?
Yeah, sure. So in the setting that you are talking about, suppose that we just like use the word summarization colon or something as the prompt. Then there are two versions here. The first version is that we just use it as it is, like use the same model parameters and just plug in summarization colon as the prompt. In that case, similar to what we discussed before about in-context learning, it will not work for small-scale models like GPT-2. Because essentially it's the same setting as if we are trying to apply in-context learning to GPT-2 models. Like we would use GPT-2 parameters to compute the prefix vector or the latent activations for the prompt word. And then if we directly use them, they will not lead to good performance. Like it might just lead to some weird artifact or some strange continuations that are not summarizations. Whereas a second option is that we could fine-tune that way. Like you could prompt it with a nicely designed set of task instruction, and then jointly fine-tune the model the same time you are prompting it. In that case, that's more similar to the PAT style, like the few-shot learning with pattern matching style model that people have, that is also quite popular recently. And in that case, we regard it more as a fine-tuning approach. It's not even lightweight. It's more of a fine-tuning approach than like our attempt to try to make the model more lightweight and have more of a prompting intuition by preserving the model and tuning the prompt.
Right. I think I interrupted you earlier when you were talking about the training details to ask some higher level questions. So maybe we can go back to the training details.
Oh, yeah. So like basically, previously I was talking about the objective at training time. So essentially the objective is the same as the fine-tuning objective. They are both using cross-entropy laws of P of y condition on x, except that now the set of trainable parameters is different. So here we are holding the language model parameter fixed, and we are only optimizing the prefix parameters that we store in p theta. And this difference leads to like a large reduction in the parameters that we need to store because we are phrasing the language model parameters, so we don't need to store them anymore. And we only need to store p theta, which is a small matrix.
Cool. Yeah, that makes sense. So I think it's clear to me how exactly training works. There's one question I had related to some detail that I saw in your paper, though. You say that directly optimizing the prefix parameters does not work directly, and you reparameterize that using an MLP. Can you tell us a little bit about that?
Yeah, sure. So this is more of an optimization trick that we find to be useful. So like instead of optimizing the p theta matrix directly, in this optimization trick, we reparameterize p theta matrix with a small matrix and a large two-layer MLP. So this trick is actually not very intuitive because we might expect a shallower network to be easier to optimize. But from a high level, I believe that this trick is effective because we are over-parameterizing the matrix parameter by a large MLP. And this over-parameterization idea could make optimization easier, as shown in some past work from Princeton about like the advantage of over-parameterization even in a linear model or even in a very simple setting. So I guess one thing to note here is that although we are over-parameterizing a bit at training time, after we finish training, we only need to store the final p theta matrix, and we do not need to store any of the intermediate MLP that we need for over-parameterization. And because we don't need to store those large MLP, we kind of maintain the storage efficiency.
Did you need to tune the size of this network you use for reparameterization?
I actually didn't tune the size that much. I kind of just pick like 512 and set it that way, and it works. So I didn't try much hyperparameter tuning in that sense.
Yeah, that's actually cool because then it works across the different settings you tried. Otherwise, it might require that we tune these hyperparameters for every prefix we want to train.
Yeah, definitely.
So just a couple of questions about why optimization might be unstable. So, right, is it that when you already have a large network with the rest of the weights in a certain state, you add this prefix drawn from, say, a random distribution of weights? They're very different from the rest of the weights. Do you think that's why optimization is kind of unstable here? Do you have any intuitions on why that might be the case?
Yeah, definitely. So I think it's probably one possible explanation. Like we didn't delve very deep into this question, but intuitively, it could be that because when we try to randomly initialize, it lies in a very different space than like if we are actually like processing words and computing these latent activations. However, I guess like even if we like initialize with some word and then pass that word through the GPT-2 model to compute these latent activations, even in that case, like directly optimizing this is still performing slightly worse than the over-parameterization idea. So, so it kind of means, it kind of rules out a little bit about the previous intuition that maybe it's because it lies in a different space. But I would say like lying in a different space would probably account for part of the reason why it's not performing well or it's not stable. And then the over-parameterization would count for like another perspective.
I see. Yeah, that's interesting.
And then essentially like, even if we don't do any strange initialization trick, just random initialization using the reparameterization trick will be effective in terms of performance in full data setting.
Okay.
Yeah.
Right. So, and if over-parameterization was making training more stable, does that mean that with greater prefix lengths, you had less of a problem because you already have more parameters there?
Do you mean like, so there are two axes here? Do you mean like with more prefix lengths, well, we are also doing over-parameterization, or with more prefix lengths, well, we drop over-parameterization?
More prefix lengths when you drop over-parameterization.
I see. Well, we actually didn't explicitly try that setting, but my intuition is that like over-parameterization would mean a lot more parameter tuning than if you like double the size of the. So here's the story. When we try to over-parameterize, the number of trainable parameters at training time would be probably equal to like the number of trainable parameters that adapter tuning would use, except that like we just don't need to store them, and then most of the parameters are not effective because the only effective thing that will affect GPT-2 would be the result of the parameterization. However, like by doubling the prefix length, it does not lead to such a over-parameterization effect as if we are using MLP. So like they are still kind of different in terms of the scales of parameterization.
Okay, cool. Thanks. That's good to know. Right, and
I guess like another point to add is that like if you just decide to directly use the like without any overparameterization, just try to directly optimize p theta, it would still work. It just requires a very different set of parameters and lead to a slight performance drop. It's actually not a very large gap. So if you really have like training time memory constraints or training time parameter constraints, you could directly optimize p theta and willingly suffer a little bit of performance drop. In that case, one thing to note is that you will just need a very large learning rate. So previously with the overparameterization trick, the learning rate that's useful to set is like 5 times 10 to the negative 5. Whereas without the overparameterization, if you directly optimize, the learning rate tend to be like 0.001 would probably be a good candidate. So it's wildly different in terms of the range for learning rates.
Since someone already mentioned it, can I ask how you choose the length of the prefix?
Oh, yeah, sure. So I choose the length of the prefix with a budget in my mind. So I want it to be less than 0.1% total parameters while maintaining a certain performance. So I have like some experiments in the ablation study part that tries to plot how the prefix length affects the overall performance. And the general takeaway is that like there's a threshold above which it would hurt performance and below which it would help performance. And in that case, the threshold is like empirically 10 for table-to-text task. So we kind of pick around 5 or 10, depending on the performance on dev set, on the validation set.
Thanks. And these vectors are then randomly initialized, or do you have any other procedure for that?
Yeah, these vectors are then randomly initialized.
Okay, since you mentioned table-to-text task, I think that's a good segue to talking about the experiments and the actual tasks and baselines you experimented with.
Sure.
Yeah, can you tell us about the 2 tasks that you describe in the paper?
Yeah, so we experiment with 2 tasks. One is table-to-text and the other is summarization. So table-to-text is essentially like you have a data table and then you are supposed to like generate some textual description of the table that are faithful to the table and fluent in terms of like quality and English. And for summarization task, the idea is that you are given a very long news article or document, and you are trying to summarize it to like 1 sentence or 2 sentence short summarization. And in the experiment, the baseline that we considered include full fine-tuning just the top K layers of the language model, and adapter tuning with different parameters levels. So we tried 3%, which is equal to the common setting in adapter tuning, and we tried 0.1% just to have a fair comparison to prefix tuning. And we also considered different tasks, different task settings, including the full data setting, the low data setting, and the extrapolation setting.
Yeah, thanks for the overview. Can you tell us why exactly you chose these specific 2 tasks?
Yeah, sure. So we choose the table-to-text and summarization tasks because they are very popular natural language generation benchmarks with quite standard automatic evaluation metrics. So the automatic evaluation metrics are not perfect, as we all know, but they are kind of well established compared to other generation tasks, such as story generation or question generation, which are more open-ended and therefore harder to evaluate. So like the choice is also supported by like a recent generation benchmark paper called GEM, like GEM, where 9 out of 11 datasets that belong to that benchmark also belongs to the 2 categories. Like they are either table-to-text or summarization.
In terms of what you expect from the model, are there any interesting differences between these 2 tasks?
So the 2 tasks are quite different and covers a diverse set of things. So in the table-to-text task, the idea is that you have a quite unnatural linearization of the table because like for a GPT-2 model, it cannot take in a structured table as the input. Instead, you need to figure out some heuristics to linearize it to make it like a sequence. And then in the table-to-text task, the input length and the output length is roughly that input is slightly shorter than the output because the table, after you linearize it, tend to be shorter than the utterance that you generate. And then in contrast, for summarization task, you have a very long input because your input would be a news article. and then you have a relatively short output. So in the scale of the data set that we consider, you kind of have like a length 400 input and a length like 30-ish output. And then additionally for summarization, it's probably a harder task to think of because during the encoding phase, like when you try to encode the input, you also need to like kind of extract the useful content that you really want to put in your summarization. So there's kind of one step where you need to do some information selection about what to keep in your summarization. And then there's another step of trying to like generate condition on the information that you extract from the input documents, and then to phrase the summarization in a fluent English sentence. Whereas in table to text, you don't really have the selection, the information or the content selection phase. I mean, like in both models, there is no explicit step for information selection, more like describing a high level of what the model should do.
Yeah, of course, that makes sense. Okay, so let's talk about the main trends in the experimental results. Let's talk about table to text first. Can you briefly describe to us what the results were like?
Yeah, sure. So like basically the main trend is that like in table to text with 0.1% trainable parameters, prefix tuning can like perform equally well, being comparable or even outperforming fine tuning and adapter tuning in the full data setting. And in low data settings, prefix tuning on average would also outperform fine tuning. And then an extrapolation setting, this is quite interesting where we are trying to like train a subset of topics and test on a different subset of topics to create some out-of-domain test distribution. And then even in the extrapolation setting, prefix tuning also shows a very strong performance gains compared with fine tuning. And simultaneously, adapter tuning is also outperform fine tuning.
I think it's quite remarkable that prefix tuning would outperform even fine tuning in some settings.
Mm-hmm.
So, right, I mean, I guess one would expect that in terms of the performance, in terms of efficiency, prefix tuning would definitely do better. I mean, that's obvious, right? So can you give us an intuition of why prefix tuning is even outperforming fine tuning in some of these cases?
Sure. So I guess like prefix tuning is like, so let's start it this way. A table to text setting, in the full data setting, we kind of observe comparable performance. And then the idea or the intuition behind this comparable performance is that it suggests that by only tuning the prefix, it is expressive enough to be able to adapt GPT-2 to this table to text task. And for the reason why it's outperforming fine tuning in some settings, to be more precise, I would say like it's outperforming in the extrapolation setting and it's outperforming in low data setting. I think my big intuition is that because it optimizes a smaller set of prefix parameters. So prefix tuning might be less likely to overfit to a small training set as in the low data setting, and therefore is more likely to keep the nice language modeling capacity derived from the pre-trained parameters. And so for the extrapolation setting, where it's kind of a more interesting and a different story, because we now have a in-distribution training data and an out-of-distribution test data. In this case, the idea or the intuition is that because we are freezing most of the language model parameters, prefix tuning and adapter tuning both have this property of freezing the pre-trained model parameters. So we are kind of better preserving the information that's attained during the pre-training phase. So for example, we know that GPT-2 is pre-trained on a wide range of corpus, and the pre-training corpus might cover a wide range of domains. So it naturally has a better ability to generalize across domains because at the pre-training stage, it's trained that way. And then by only doing fine-tuning, we are then only initializing the model with prefix with the pre-training weights. And then maybe there is a much better way to exploit the pre-trained model than simply copying during the initialization part. And basically, like if we freeze all the pre-trained model parameters and instead optimizing only the prompt, it is one way of trying to exploit more from the pre-trained GPT-2 model or from the pre-trained language model in general. And therefore, we should probably expect some performance gains in terms of extrapolation because we're preserving the original pre-trained model more.
Okay, yeah, that makes sense. Before we talk about the results from the summarization experiments, is there anything else that you think is worth pointing out in the table to text experiments?
I think that's mostly everything that I want to point out in table-to-text. By the way, we experiment with 3 table-to-text datasets that are of quite different style and quite different domains. So the smallest dataset we looked at is E2E, which is only about restaurant. And then the larger datasets include web NLG, which is more open-ended, but still contains around 15 topics in total. And then there is the more open-ended web datasets on Dart, which includes some Wikipedia table, so making it open-ended. And the takeaway is that prefix tuning kind of extrapolates to all these 3 datasets and work well with a wide range of domains.
Perhaps you have already mentioned it. Can you reiterate why prefix tuning with the same number of parameters as the adapter is performing a little bit better, where this parameter efficiency comes from?
Yeah, that's a great question. So let's first iterate about their similarities and then why they are different. So while prefix tuning and adapter tuning both phrase the pre-trained parameters, they actually tune different sets of parameters and affect the activation layers of the transformer differently. So prefix tuning uses the pre-trained attention block to compute the activation vectors for each prefix vector and therefore affect the subsequent activations in a similar style as if they are prompting. Whereas adapter tuning inserts this trainable NLP module between language model layers, which directly adds residual vectors to the activations. So we think this gain in parameter efficiency is because prefix tuning keeps the pre-trained language model intact as much as possible, more so than adapter tuning, and therefore it can exploit the pre-trained language model more. So this is more of an intuition of why it works. And then we don't really have the detailed comparison or the theoretical analysis of how this different inductive or this different architecture design leads to different performance.
Got it. Thank you.
Mm-hmm.
So let's talk about the summarization experiments. Can you tell us about the data sets you experimented with and the general trends in the results here?
Yeah. So we experiment with the XSUM dataset, which is a news summarization dataset that is very abstractive in how that dataset is designed. So that's why we run abstractive summarization on that dataset. So prefix tuning does not outperform full fine-tuning in this case when we only have 3% parameters or when we only have 0.1% parameters. But we still see gains in low data settings, and we still see gains when there is a topic mismatch, or i.e. in the extrapolation settings. So to follow up on the slight performance degradation of the summarization in the summarization dataset, we think that this is the cause is related to the encoder capacity. So basically, when we run an ablation experiment where we allow the encoder parameters to be fine-tuned, but the decoder parameters to be prefix-tuned, then the results get improved and becomes comparable to the full fine-tuning results. So as for the low data setting and the extrapolation setting where we see a performance gain, I think theoretically, these are still open problems of why there is this, exactly why there is this gain. But basically, my intuition would be the same, that we talked about low data and extrapolation before, that prefix tuning plus initialization trick or some sort in the low data setting would actually kind of avoid the overfitting issue or alleviate the overfitting problem in both summarization and table to text. And then similarly, the intuition is true for extrapolation.
Okay, cool. So, okay, that's good to know. I think you also brought up one interesting detail here. You talked about prefix tuning on encoder versus decoder.
Mm-hmm.
I don't think we talked about that specific detail earlier.
Oh, yeah, sorry. So basically, we run the summarization experiments using the BART model.
Right.
Because if we also tried preliminary experiments running summarization using GPT-2, and it's quite suboptimal compared with this type of sequence-to-sequence model. So therefore, we switch it to BART. And then when we try to implement prefix tuning using the BART model, the idea is that we would prefix tune both the encoder and the decoder. So we would prepend this trainable prefix at the beginning of the encoder, and simultaneously we would prepend it at the beginning of the decoder. And then we would train the 2 sets of prefix jointly, the encoder prefix and the decoder prefix.
Okay, yeah, that's very interesting. Yeah, thanks for the clarification. Okay, right. So you talked about the general high-level trends in both the summarization and the table-to-text experiments.
Mm-hmm.
Do you want to talk about any ablations that you ran, any other interesting trends in these experimental results?
Yeah, sure. So I guess we kind of talked about the first ablation before. The first ablation is about like the prefix lens, how the prefix lens would impact generation performance. And then intuitively, the takeaway is that increasing the prefix lens is helpful up until a certain point. And then the threshold would be task dependent. So it's 10 for table to text and around 200 for summarization. So if we increase the prefix lens beyond this point, it would lead to overfitting, and that would lead to a performance drop therefore. And the second ablation that we studied is like how trainable vectors position would affect the general performance. So in prefix tuning, because of the word prefix, we are actually putting the trainable parameter in front of, at the very beginning, like in front of the input and output x and y. So in this ablation study, we also tried placing them in between the input and output. Like, so we would have like x and some trainable parameters and then y. And we call this infix tuning. So the takeaway from this ablation is that infix tuning slightly underperformed prefix tuning. We believe that this is because prefix tuning can actually affect the activations of both x and y, whereas infix tuning can only influence the activation of y because we have an autoregressive model where the right context is able to attend to the left context, but not vice versa. So when we place the trainable parameter in the middle, y can attend to the trainable parameters, but x cannot attend to trainable parameters, leading to like a drop in expressiveness. And another ablation study that we have is the embedding-only ablation. So in this case, we only train the 0th layer of the prefix, aka just the embedding layer. Whereas in prefix tuning, we make all layers of the prefix activation trainable. So for example, in GPT-2, there are 12 layers, and our prefix is consisted of the prefix activations at all 12 layers, whereas the embedding only will only take in the bottom one layer. So the takeaway from this experiment is that tuning only the embedding layer is not sufficiently expressive for generation tasks because it suffers a relatively large performance drop compared with prefix tuning.
Cool. Yeah. Thanks for that overview. I think I think the experiments in your paper are really thorough, and I really enjoyed reading the experiment section.
Thank you.
Right. So to understand the general takeaway from these experiments and your paper in general, where do you see prefix tuning helping in what cases going forward? So
I see.
Clearly, prefix tuning is an alternative to fine tuning, right? In what cases do you think we should use prefix tuning instead of fine tuning?
Yeah, that's a great question. So basically, like, let's talk about it from two perspectives. From a performance perspective, we just kind of use the takeaway from the experiment section. I expect prefix tuning to work well in a low data setting or in an extrapolation setting. Moreover, when a task requires a simple encoding but a more complex decoding, as in the case of table to text, I think prefix tuning will be more favorable. And from the second perspective would be like a storage perspective. So from a storage perspective, we can imagine some interesting computing paradigm where maybe in the future, the pre-trained model really gets too large to be stored or fine-tuned in a standard local compute. So now we can imagine that there is some cloud device with GPU that stores the large pre-trained language model. And all the users will just query this language model for output values, intermediate values, or even gradient information via some API. It's like similar intuition to the GPT-3 API, except that it's also giving gradient information and some more intermediate results. And then fine-tuning becomes infeasible in this setting because it would be too expensive to tune or to store a local copy of the very large model for each task. So instead, in this case, prefix tuning will be quite useful in this setting because the local prefix is small, and then all that is required is to query the gradient information from the cloud device. And the overall memory footprint locally will be very small as well. And well, suppose that we can also imagine another setting where instead of scaling up the model size, where instead we are now scaling up the number of users, or i.e. the number of tasks. So suppose that we are in a setting where we care a lot about personalization or user privacy. So if we fine-tune the model for each user, as the number of users scales up, it will be very expensive to store a personalized model for each user. So if we switch to another direction, say like now we want to merge user data and then store a large joint model for all the users, then we are sacrificing user privacy because we are mixing up the user data. And then in this case, if we actually switch to prefix tuning, then we kind of have the best cases of both worlds where the overhead for each additional user is very small because we only need to save the personalized prefix, which is quite small. And therefore, we can easily scale up to a large number of users. And also, we only need to store, and also like we are not leading to, like, we are not sacrificing user privacy because we can preserve user privacy by avoiding cross-contamination of user data, since the prefix are trained independently of each users.
One point you made, I think about a minute ago, is about the complexity of encoder versus decoder. And if tasks require not very complex encoders, but slightly more complex decoders, prefix tuning might be more helpful than fine tuning. I didn't quite follow that intuition. Can you please elaborate on that? Why do you think that might be the case?
I see. Yeah, so I guess it's not like more, so it's more of the intuition that we get by comparing table to text and summarization. In summarization, a more burden is put in the encoder side because like we need to use the encoder to be able to extract the right information or the useful contents that we will then use for summarization. Whereas in table to text, the encoder is doesn't have much burden because it will just figure out the right way to encode all the table contents. And then the decoder will be in charge of grouping them in a natural way. So the takeaway here from comparing the two tasks, and also from the additional experiments, that if we fine-tune the encoder, it leads to a performance improvement in the summarization setting, means that when we require the encoder to perform a complex task, such as extracting important information in summarization, prefix tuning is not that effective, or prefix tuning is kind of the bottleneck that leads to performance drop. Whereas if we actually fine-tune that encoder and still keep prefix tuning for the decoder part, we kind of get performance improvements, if that makes sense.
Okay, yeah, I think that does make sense. Yeah,
I think like just to like follow up on some recent work that's also very related to prefix tuning. There's a paper recently called P-tuning, which tries to like adapt GPT-2 for some natural language understanding tasks, basically the super glue benchmark. The takeaway is that they actually jointly do prefix tuning, or they call it P-tuning, and fine tuning for better performance on the NLU benchmarks, suggesting, well, I mean, intuitively, if we regard the NLU tasks as an encoder-based task, it kind of suggests that when we try to tune an encoder, maybe like P-tuning plus fine-tuning jointly would be most effective. And similarly here, for the encoding of the summarization information, maybe like fine-tuning would be a better option.
Do you know whether they also had this evaluation setting where they tested the generalization of this approach, and whether like combining fine-tuning and prefix tuning also gives us benefits that you showed with prefix tuning?
By generalization, you mean extrapolation?
Yeah.
I don't think that paper includes that part.
That would be interesting.
It's definitely very interesting future work. Yeah.
I had one last thought from benefits discussion, which is unrelated to fine-tuning, and that is, can we use these continuous vectors that you learned with prefix tuning to kind of figure out automatically whether we can transfer across certain tasks? So basically, if two vectors are similar, we can say, oh, these two tasks are similar, so maybe we can fine-tune the model on one task for the other. Do you have any thoughts about that?
Interesting. So like this is a really interesting question. So whether continuous prefix learned by prefix tuning can be used to predict transferability across tasks. I don't really have a gold answer for it, but I have some intuition or guesses. So we might expect that like we could define some similarity metrics in the prefix vector space and maybe conclude that high similarity leads to high transferability. But just to point out some possible issues with the naive approach, because when we train using different data sets, using the same data sets but different random seeds, the resulting prefix will still be quite different in L2 space already. So maybe it would suggest something like maybe L2 space is not good enough as a similarity matrix. Maybe like we should really study the similarity matrix in some more latent or meaningful space. But I guess the general takeaway is that, I mean, even if we are using the same data set but like different random seeds because of training and initialization issues, like there might be multiple prefixes that are equally good or that are similarly good. And then if those prefixes are distributed quite far away in a similarity matrix, then maybe like the naive approach is not satisfying, or it's not going to really predict transferability, because when training on the same task, it should have the highest possible transferability. Right?
Yeah, that's a very good point. Maybe we can just do something silly and average 10 prefixes for the same task.
Yeah. Well, it depends on the landscape of the prefix space.
Totally.
Yeah. But in general, I think the transfer idea is very interesting. So like there actually could be many different types of transfer. So like the first one is that we could think of transferring the prefix learned from one model to another model, maybe like from GPT-2 medium to GPT-2 small. And here the caveat is that, well, first it does not type check, because GPT-2 medium and small has very different activation dimensions and embedding dimensions. So we might need to still learn some transformation to apply to the prefix vector to be able to map it to the right dimension. But dimension is actually not the only problem. So I mean, like suppose that you have GPT-2 small and GPT-2 small copy where they are trained using the same data but different random seeds. And then it's very likely that like the embedding of Apple is going to be very different for GPT-2 small and GPT-2 small copy. And then in this case, it's not just a dimension problem, or it's not just a type checking problem. Then like it's more about like the prefix of when we train it on different models will lie in different subspace, maybe. And then in that case, like a really careful mapping from the first model's embedding space to the second model's embedding space might be helpful in terms of how we transfer across models.
Yeah. Thank you so much.
Yeah, thanks. That's a great discussion. All right. Yeah, that's all the questions I had for you. Is there anything that you wanted to talk about that I didn't ask you about?
I think that's mostly it. You asked great questions.
Well, thanks a lot for this fun discussion, Lisa. I think this is a really cool paper. Thanks for joining us.
Thank you.